Okay, so I'm trying to record on my Mac, but I can't get the mic to work quite right. So let's give it another try. So I've got this system of differential equations. Derivative of x with respect to time is equal to x plus y. Derivative of y with respect to time is equal to 4x plus y. So here, this is a linear system of differential equations with constant coefficients. Matrix-wise, I could say I have this vector x, which is xy, dotted, derivative with respect to time, is equal to the coefficient matrix 1, 1, 4, 1 times the vector x. Writing down the eigenvalue determinant matrix, here I have 1 minus lambda 1, so I'm just taking lambda away from here and here. 4, 1 minus lambda, cross multiply and subtract leads to this characteristic equation. Shortcut on the characteristic equation is that you'll always have lambda squared minus the trace. The trace is the sum of the numbers in the main diagonal of the coefficient matrix. Then plus the determinant. The determinant is always the main diagonal minus the other diagonal. So 1 times 1 minus 4 times 1 gives negative 3. Setting that equal to 0 and solving leads to lambda equals 3 or negative 1. If lambda is 3, plugging that in here, 1 minus 3 is 2. As far as the eigenvector is concerned, a1, a2, I would have 2, or let's see, 1 minus 3 would be negative 2, excuse me, negative 2a1 plus 1a2 is equal to 0. a2 then equals twice a1. So the first eigenvector related to the eigenvalue of 3 is 1, 2. If we let a1 equal 1, a2 would have to be 2. So we just want a simple version of the vector. We need the direction. Over here, our second eigenvalue is negative 1. Plugging that up in here, 1 minus negative 1 is 2a1 plus 1 a2 equals 0. Solving for a2 gives a2 as negative 2a1. If a1 happened to be 1, a2 would be negative 1, and so one version of the eigenvector is 1, negative 2. We want the direction. That's a simple version of that direction. So the vector solution here would be some constant times the eigenvector 1, 2 times e to the 3t, 3 being the eigenvalue that led to that eigenvector. Similarly, add that on to c2. Eigenvector is 1, negative 2 times e to the negative t, negative 1 being the eigenvalue that led to that eigenvector. We can then rewrite that as x of t is c1 e to the 3t plus c2 e to the negative t, this being 1 and 1 for x. Down here I have 2 and negative 2 for y, so y of t is twice c1 e to the 3t minus 2c2 e to the negative t. What I want to do next is take a look at, for various values of c1 and c2, what do the solution curves look like? How does that relate to a slope field? Slope field here, dy dx, slope would be y prime over x, y dot over x dot, which according to my system would be 4xy, 4x plus y over x plus y, slope. If t is increasing, as far as these solution curves are concerned here, e to the 3t dominates. For big values of t, this is large, that is approaching 0. If t is negative but large, away from 0, then this guy will be a big positive number, and this guy will be negligible. And so that's going to dominate the system when t is negative. So what that should lead to is a set of solution curves that look like this. The blue is the first eigenvector, 1, 2. Since the eigenvalue is positive, we're heading away from the origin on either side. The other eigenvector was 1, negative 2, which puts us on this red line. And since it has a negative eigenvalue, that means we're heading in toward our origin from either side. So solution curves, if we started here, would be following close to this line, then the blue line is going to pull them away as time goes on. Because again, for values of time that are greater than 0, the blue one is dominant. For values of t that are less than 0, the red eigenvector is dominant, which means the solutions are near it. So if you pick a point anywhere, like over here, the solution is going to be near the red eigenvector at first, and then it's going to diverge and head toward and parallel to the blue eigenvector as time goes on. Now, it doesn't mean it's an asymptote. Right? For large values of t, it will just be parallel to it. So it's possible if I started at a point out here that my solution curve is going to be parallel to the red one at first, but the closer I get to the blue one, I'm going to be pulled in each direction. Whoa, that's a messy one. And so I'll be heading like that. And what these curves are going to look like. Let's take a look at the slope field. Slope field, right here, I typed in dy dx equals numerator parentheses 4 times x plus y, close parentheses, divide by parentheses x plus y, gives us this right here. And you can see that eigenvector here, that was my red one. My blue one would be pretty much like this direction right there. So you can kind of see the relationship between the slope field and the solution curves. They look pretty similar. Thanks. Hopefully this recording works. And I am going to do one on complex eigenvectors and their phase planes next.